Hey everyone, and welcome back to Talk Tensors. Today we're going to be diving deep into a paper called Entropy-Regularized Wasserstein Barycenters for Synthesis and Analysis of Probability Measures.
Oh, yeah.
It's a mouthful.
Yeah, that's a long one.
But the concepts, I think, are really, really elegant.
Yeah.
And we're going to unpack why this paper is causing such a buzz in the ML community
Yeah.
and kind of trace the lineage of ideas that led to it. And then, as always, we'll finish off with some novel notions
Yeah.
to ponder.
Looking forward to it.
Awesome.
So,
This is a paper that definitely gets you thinking.
yeah.
At its heart, it's tackling this problem of how we work with data sets where each data point isn't like a simple number or a vector, but it's a whole probability distribution.
Right. Instead of looking at individual ingredients, we're trying to understand like a whole recipe.
Yeah, exactly.
Seems like a pretty radical departure from how we usually think about data.
It is.
So why is this distributional perspective gaining so much traction these days? I think it's all about like trying to represent the data in a way that captures more of its inherent complexity. So like, signals, images, text, all these can be viewed as probability distributions and allows us to capture not just like the individual values, but also the uncertainty and variability within the data itself.
So instead of just seeing a static snapshot, we're capturing like the whole spectrum of possibility.
Exactly. And then that opens up all these new avenues for synthesizing new data and analyzing existing data in a way that's much more nuanced than traditional methods.
Okay, I'm starting to see the potential here. But before we get into the specifics of this specific paper, I think it'd be helpful to understand like the historical context a little bit.
Yeah.
What were some of the earlier attempts to deal with data as probability distributions?
Well, initially people tried adapting, these classic techniques like PCA and NMF, principal component analysis, and non-negative matrix factorization.
Right.
But these methods often struggled when the distributions were complex or didn't overlap neatly. They kind of missed the forest for the trees by focusing too much on individual values and not enough on the overall shape of the distributions.
So they were trying to fit square pegs into round holes.
Exactly.
Yeah.
So what really changed the game was the introduction of the Wasserstein metric.
Okay.
And this provided a way to measure the distance between distributions that really took into account their shapes and spread rather than just comparing individual points.
So it's like measuring the distance between two recipes based on how much you need to change one to transform it into the other,
Yeah.
instead of just looking at whether they both use salt.
Perfect analogy.
Yeah.
Yeah. And so that led to the development of Wasserstein Barycenters, which is a way to kind of find an average or representative distribution for a set of distributions.
Okay, that makes sense. But this paper introduces something called entropy-regularized Wasserstein Barycenters.
Yeah.
So what's the entropy-regularized bit all about?
That's the real magic of this paper. It turns out that regularizing these barycenters with an entropy term makes them much more stable and computationally tractable,
Okay.
especially when you're dealing with high-dimensional data, which is pretty much the norm in ML these days.
So not only do we have a more sophisticated way of like looking at data, but we also have the tools to actually work with it efficiently.
Exactly.
This is starting to sound like a real game changer.
Yeah, it definitely is. So this paper really builds upon these earlier ideas and takes them to a whole new level, and that's what we're going to be digging into next.
Awesome. I'm excited.
Yeah, me too.
All right, so we've set the stage with the why and like the historical context.
Yeah.
So let's dive into the heart of this paper. Like, what exactly are these entropy-regularized Wasserstein barycenters?
Right.
And what makes them so special?
So in essence, they give us this really powerful way to synthesize and analyze data that's represented as probability distributions.
Okay.
So imagine you have a collection of like reference data sets, each with its own, unique distribution. These barycenters allow us to create new data points that kind of blend the characteristics of those references,
Okay.
like creating a hybrid recipe that combines elements from multiple cuisines.
So it's not just about finding the average, but about creating something new that reflects the essence of those original data sets.
Exactly. And then on the analysis side, these barycenters help us to understand how a new data point relates to those reference data sets. It's kind of like reverse engineering a dish to figure out its key ingredients and their proportions.
That's a great way to put it. It's like breaking down a complex flavor profile into its like constituent parts.
Yeah.
But how does it actually work in practice?
Right.
The paper mentions something called the Sinkhorn Barycenter functional.
Yeah.
Is that the key?
That is one of the core mathematical tools that they introduce.
Okay.
It's essentially a formula that defines how to calculate these special barycenters in an efficient way. And it takes advantage of a technique called Sinkhorn iterations, which makes it way faster than like traditional methods, especially for high-dimensional data.
So we have a way to represent data as distributions, a metric to measure the distance between them,
Right.
and now an efficient way to actually calculate these representative barycenters.
Yeah.
What's next?
So one of the key contributions of this paper, I think, is its focus on sample complexity.
Okay.
In machine learning, we're always concerned with, how much data do we need to get reliable results?
Right.
And this paper proves that thanks to the entropy regularization, we can estimate these barycenters with relatively small amounts of data, even when the number of dimensions is very large.
Wait, so we're like avoiding the curse of dimensionality.
Exactly.
That's huge.
It is. It means that these methods can be applied to like real world data sets without needing, mountains of data.
Right.
And they also provide theoretical guarantees about the accuracy of those estimates.
Okay, this is all incredibly impressive. But I'm curious, how do we actually use these barycenters for analysis? The paper talks about barycentric coordinates.
Yeah.
What are those?
Think of them as a sort of fingerprint for a new data point.
All right.
They tell us how much each reference distribution contributes to that new point.
Okay.
It's like getting a percentage breakdown of each ingredient in our recipe analogy.
So it's not just about finding like a representative average,
Right.
but also understanding the unique composition of each data point in relation to those references.
Precisely. And the paper introduces an algorithm that can efficiently calculate these barycentric coordinates.
Okay.
And they even show that these coordinates are relatively stable, meaning that they're not overly sensitive to noise or errors in the data.
So we have a robust and efficient way to analyze how individual data points relate to a set of reference distributions.
Exactly.
That seems incredibly powerful. Did the authors demonstrate any specific applications of these techniques?
They did. They applied these methods to the problem of classifying point clouds, which are essentially collections of 3D points that are used to represent objects.
Okay.
And they showed that by using barycentric coordinates, they could create a classification system that outperformed other popular methods, especially when the amount of training data was limited.
So they're not just theoretical constructs, they actually work in practice.
Yeah, exactly.
That's really exciting. This paper seems to be like pushing the boundaries of how we think about and work with data. But before we wrap up, I'm really eager to hear your novel notions.
Yeah, okay.
What new ideas has this paper like sparked for you?
All right, let's get into it.
This paper has like really sparked my imagination.
Yeah.
It's amazing to think about all the potential applications of these techniques.
Mm,
But you know me, I always like to push things a little bit further.
yeah.
What if instead of just analyzing individual data points as distributions, we looked at like entire data sets that way?
Yeah. Oh, that's a fascinating idea. It's like taking a step back and considering the overall like flavor profile of a whole collection of recipes
Exactly.
rather than just like focusing on individual dishes.
Could we use these barycenters to compare, cluster, or even classify entire data sets based on their like distributional characteristics?
It's definitely a possibility worth exploring.
Yeah.
Imagine being able to compare like the distributions of customer behavior across different market segments,
Right.
or analyze the distributional patterns of gene expression in different populations.
Or even comparing the results of different scientific studies based on the overall distribution of their findings.
Yeah.
It's like opening up a whole new dimension of analysis.
Yeah, I think this paper provides the building blocks for that kind of thinking.
Hmm.
It's not just about analyzing data points in isolation, but about understanding the relationships and patterns within entire data sets at a distributional level.
This is really mind-blowing stuff. It feels like we're on the verge of like a paradigm shift in how we think about and work with data.
I agree. This paper is a call to action for researchers and practitioners to embrace this new distributional perspective. The tools are there. Now it's time to get creative and explore the vast possibilities they unlock.
Well, you've certainly given me a lot to ponder. Thanks for guiding me through this incredible deep dive.
My pleasure. Always exciting to discuss these cutting-edge ideas and think about the future of data science.
Listeners, be sure to check out the show notes for links to the paper and any other resources that we mentioned. And to all our listeners, thanks for joining us on Talk Tensors. We'll be back next week with another exciting paper, so stay tuned.
See ya.